Okay, so we're going to look at two sections today, and the good news is there'll be no calculations, so you won't have to use our calculator for anything. There will be a bunch of extra videos that you can check out and watch that'll help add some more substance to what we're going to look at. So the first section is section 9.3, and if you're a musician, you might know something about this already, and it's called beats or bad tuning. And when we have instruments or even smaller things like strings on a guitar, when they're in tune, the sound is very nice. It's together. It's always difficult to describe some of the musical arts because you end up using words that are non-scientific, quantitative. They're more qualitative ways of describing. So when we talk about tuning, we can put some little quantitative values into this. And this really helped me understand tuning, is that when you have two sounds being produced, and I'll try and show you a little demo with some tuning forks and maybe some other instruments, when they're playing the same note identically, you can't actually tell which one is creating the note, or both of them are. When they're in perfect tune, it sounds like one instrument. And that's really important. Okay, so when things get out of tune, you can actually hear the differences, and you hear it as a beat. You hear it as a wobble, a whoop, 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 whoop kind of sound. So if we look at this one here, the top picture is two separate sounds, and you can see very clearly that they're out of phase. Okay, they're totally not in phase. There are parts that are close. If these were perfect waves that were in phase and everything was ideal, everything would look like that, and you would take this pattern and you would just keep duplicating it. Okay, and you would never know that they're out of phase. Everything would sound perfectly. But when they are out of phase, like these two are, you start to get your constructive and destructive interference happening. So right here you can see there's some destructive interference. You've got a crest and a trough canceling each other out. And it's that element which creates this fluctuation in the sound. Okay, and then what we hear is like a beat or a wobble in the sound. So when you hear the tuning forks in a minute, you'll hopefully be able to hear the reader, 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 reader as those sounds kind of go up and down. Okay, the key piece with this is that the farther apart they are in their frequencies, so say one is tuning at 100 hertz, one is tuning at 105 hertz. The difference between those two is 5 hertz. So the beat frequency that you would hear is actually 5 hertz. So every second you would hear 5 beats. And as you get those two numbers closer together, that beat frequency starts to decrease. Okay, so that's what beat frequency is. It's just one way. So as you slow that down from a woo 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 woo, then you would have two sounds that are in tune. And I apologize for my poor singing, but just to give you an idea. So I'll try and show that with some tuning forks and some other things. That'll come up after this slide.
Okay, so we have those two sound boxes with the exact same tuning forks. They're both tuned to A440. If I hit them both together, you can hear that they're in phase. In fact, it got a bit louder, which we would expect from constructive interference. Okay, now I'm going to do something a little bit different. I'm going to put a small weight on this one, which is going to throw it out of phase. So all it is just a little mass. And then we screw it on top. Stop them both. And now, when we excite them with the hammer here, we should hear a difference. And you can hear they're out of tune. Okay, now my ear's not great enough to hear the wobble. Okay, so I'll do it one more time. Maybe I'll move this down just a bit. Okay, you can hear a little bit of a wobble. Okay, and I'm not good enough to count that frequency, but you can hear they're out. That's the beat frequency, or that beats for bad tuning. So they're out of phase, and that constructive and destructive interference is happening to create that up and down sound. Okay, so this is a bagpipe, or at least the top of it, and I just want to focus on these two pieces here. These are called drones. This is a bass drone, these are tenor drones. So I'm going to blow this up and you're going to hear these two are going to wobble a lot, and I'm going to move them between being in phase and out of phase, and you should be able to hear the beat really easily on the bad tuning side. There you are.
And for this section, it's really short, section 9.3, 1 and 2. And I'm going to keep moving to section 9.4. Okay, so now two words we want to know when we're talking about waves: damping, and resonance. Okay, damping is a reduction in the amplitude of a wave as a result of energy absorption or destructive interference. And you've probably experienced this in your lifetime. In fact, I can guarantee you've experienced this in your lifetime. Something even as simple as a swing. So if you are pushing a child on a swing, or you hear the child being pushed on a swing, as long as someone keeps pushing you just a little bit, you can normally maintain a fairly steady, periodic, perfect behavior on that swing. You go up to the same height, you come back down. You get a little push, you go back up to the same height. But when the person stops pushing you, you'll go up to that height, and then you'll come back down, and then you'll go up, but you won't go quite as high. And then you'll come back down, and then again you won't go quite as high, and eventually you'll get to the point where the swing is just moving back and forth a tiny little bit, and you've essentially stopped at the lowest point, or the equilibrium point. Okay, and that's damped motion. Okay, and it's not always bad. Damped motion can be really helpful, and we'll talk about that in a second. Resonance is sometimes called natural frequency, or resonant frequency. It's the frequency at which a medium vibrates most easy. Okay, there are objects out there that there's a frequency they just want to vibrate at. It's if you can stimulate them at that frequency, they'll do some crazy wild things. Okay, and I have a few videos to show you of that. Resonance is the condition in which the frequency of a wave equals the resonant frequency of the wave's medium. So there's some harmony going on here. So you can see in this picture here, nothing's happening in this picture for the first 60 seconds. Okay, and then something happens right here around here. Okay, and the amplitude jumps up. So suddenly this object is not moving at all. There's very little going on. Then suddenly that amplitude of whatever this object is starts moving significantly. Okay, now this isn't a big deal as long as you stay, say, in this range. Then you never notice that this effect even occurs. Where this can be really scary or dangerous is if you're an engineer and say you're building an airplane or something, and the wings have this natural frequency they want to vibrate at, and if for some reason, wind conditions, weather conditions, speed of the airplane, design of the interior of the wing, the way it's designed, if you hit that natural frequency and the wave or the wings start to bounce up and down through these large amplitudes, and you might be surprised, wings on an airplane are actually made to stretch, to move. They fold up. That's part of how they're designed. They are elastic, but they're not designed to shake really, really fast like a bird. Okay, so that's a bad thing. So we want to, as engineers, as scientists, we want to make sure that these natural frequencies are known to us, they're known to our designs, and we can sort of mitigate whether we want to use it or not want to use it.
Okay, so this would be an example of resonance that is positive and useful. So here's a tuning fork. Okay, you can hear that's pretty quiet. So I'm going to hit it one more time. And you can notice there's a big change in sound there. So I'm just going to actually mount it here so my fingers... Okay, so I'll hit it one more time. Okay, so this box down here is a sound box. Okay, and it's serving to create those standing waves, those resonant waves, which increases the amplitude, which increases the volume for what we can hear. So one more time. Cool. Okay, so we have two of the exact same tuning forks and same sound boxes. This is just to give a little demonstration of neither one. You can hear that neither one is making any noise right now. Okay, and then I'm going to excite this one on the right hand side. And what we're going to see, and it's really kind of neat, is because they both have the same natural frequency, that same resonant frequency, this one's actually going to start vibrating even though I don't touch it. Okay, so let's see how well this works. It won't be very loud, but you should be able to hear it still. Okay, so that second sound is coming from this one. Okay, I'll stop them both. Do that one more time, so I won't touch this one. That is all that guy. Cool.
Okay, so just a quick review here of a standing wave. They're not quite symmetrical, but they definitely have symmetrical properties. They're nice, smooth flowing curves. The amplitudes are the same. They have these nodes that don't move. So when you look at these, there are 6 little pictures here, and they all look like waves, but they're not all standing waves. So the first 2 here are standing waves. Okay, they have nodes. They're nice. They're if you kind of think of it like a reflection about it that way, they're perfect. Okay, then now C through F, they look very similar, but they don't have nodes. The amplitudes might be a little bit different here, here, and here. This one's easy to see. These amplitudes are very different. This one doesn't maintain its shape. This one's close, but it might. We're not actually told there's a node, so it could be doing some other things. So the only ones here that are standing waves are A and B. Okay, so just going back to that idea of damping and resonance, if you drove to school today, to work today, then you have used damping. And it's very simple. That you have springs inside your car that are attached to the axles and the wheels. So when you hit a bump, okay, your car jumps up, it comes back down, and then it settles down, and you have a smooth ride again. If you have really bad shocks and springs in your car, when you hit a bump, it'll just keep moving up and down, up and down, up and down. And that might seem really funny at first, but it's also very dangerous. Okay, so as your car bounces up and down, you're changing the effects of your tires on the ground, which can give you some issues when it comes to steering, to braking, those types of things. Not to mention after 10 minutes of bouncing up and down, you're probably going to get really fed up and annoyed with it. Okay, if you're building large buildings in earthquake zones, okay, this is one of my favorite topics. When the ground shakes due to an earthquake, it has a frequency, and you're trying to avoid matching that ground frequency to building frequency. And that's what the next few slides are about, and it's mostly videos. I'd really like you to watch them. They're really, really interesting. So as an earthquake engineer, your job is to analyze the soil, analyze the conditions that you're building on, and try and design a building that you can keep the frequency of the ground and the frequency, the natural resonant frequency of your building. You want to keep those as far apart as possible. Okay? So this is a shake test. If you can go to the PDF and click on this, you'll see there are ways that they can model. They'll actually shake the ground under a model of a building to see how it behaves. In this one, there's two buildings side by side. You might be surprised which one falls first. This one I would really, really, really like you to check or take a look at, please. This is a shake table. Okay, and you can do this in university. I've put in the time markers here because you don't have to watch the whole thing. It's about 4 minutes, but the exciting stuff happens at these markers, and you'll see there's different frequencies. There's 3 different models built on this shake table, and they all do very wild and crazy things at these 3 markers. And I'd really like you to watch that. It gives you a really good insight into how buildings behave under different vibration conditions. Okay, so if you're thinking of any kind of engineering, especially civil engineering, then that would be a good place to have a little look. Two more videos that are really cool. I don't know if you've heard of Tacoma Narrows, but this is a steel bridge that was hanging over a large waterway. Wind was blowing over the bridge. Some things happened. If you haven't seen this video, it's a must to see. It's not a resonant case. I'll give you the heads up. It's not. It was a brand new engineering phenomenon that had never been heard of or thought of before, and it was called flutter. And this is another link right here. So there's two little links here you should watch. And this is why engineers exist. They build things. They try and do their best, but sometimes there's just phenomenon you don't know about. And in analyzing how this bridge went through its process and collapsed, they came up with something new called flutter. Okay, this one's just fun. It's rice on a table. I've always wanted to build one of these, but I just haven't got around to getting the parts together. It's just fun to watch, and you'll see different resonant frequencies will do different things to this table, and you'll see the rice behave in different ways. Maybe turn your sound down a bit. It's a little loud. And okay, so damping is the condition in which the amplitude of a wave is reduced. Okay, we've got resonance is another condition where we have standing waves where you get a giant amplitude, and I'm not going to read that to you because you can pause that and do that yourself, and I'll leave you with section 9.4, 1 to 3 and number 5, and thanks for tuning in.